History, as we know, it might be completely wrong. We are about to explore 20 ancient machines that should not have existed, incredible devices that challenge our entire timeline of human progress. By the end of this journey, you will discover a hidden chapter of innovation that rewrites the story of our past. We will uncover a 2,000-year-old computer found in a shipwreck and examine a clay jar that may have generated electricity. How did our ancestors achieve such technological marvels with only primitive tools? The answers will force you to question everything you thought you knew. What does it truly mean to be an advanced civilization? The stormy Mediterranean waters off the coast of Greece in the year 1900 hid an incredible secret. Sponge divers seeking shelter from a gale stumbled upon the wreck of an ancient Roman cargo ship. As they explored the silty remains, their hands closed around a formless lump of corroded bronze and wood, indistinguishable from the surrounding rock. It seemed like just another piece of junk from a 2,000-year-old tragedy. No one could have guessed this unassuming lump was the single most important scientific artifact ever recovered from the ancient world. It would become known as the Antikythera Mechanism. For nearly 50 years, the strange object sat in a museum storage room, a complete mystery. Then, painstaking cleaning and advanced imaging techniques finally revealed its true nature. This was not a statue or a simple tool. It was an intricate, hand-powered clockwork universe, a complex system of at least 30 precise bronze gears housed in a wooden case. Inscriptions on its faceplate served as a detailed user manual explaining how to operate this ancient computer. By turning a hand crank, the user could make dials and pointers move, predicting the movements of the sun, the moon, and the 5 known planets. It could forecast solar and lunar eclipses and even track the 4-year cycle of the Olympic Games. The sophistication of its engineering is what truly stuns historians. Dr. Tony Freeth and his research team have shown that the device used a complex assembly of interlocking gears, including a unique pin and slot mechanism that accounted for the moon's irregular orbit. This was not a simple calendar. It was a mechanical representation of the Greeks' understanding of the cosmos, a physical model of the heavens. The knowledge required to design and build such a device, with gears cut to exacting tooth counts to represent celestial ratios, would not be seen again until the development of astronomical clocks in Europe during the 14th century. That is a gap of over 1,000 years. How did a civilization we associate with marble statues and epic poetry produce such a technologically advanced machine? Who was the brilliant mind that conceived of it, and what tools did they use to craft gears with such microscopic precision? The Antikythera Mechanism stands as a silent, defiant challenge to our linear view of progress. It suggests a pocket of scientific and engineering knowledge in the ancient world that was lost for millennia, a forgotten chapter in human ingenuity that forces us to wonder what else might be lying on the ocean floor, waiting to rewrite our history. While the Antikythera Mechanism redefined our view of ancient Greek engineering, a far simpler yet equally baffling discovery was made half a world away. In 1936, during excavations near Baghdad, workers unearthed a set of peculiar clay jars. Each one was about the size of a man's fist, sealed with an asphalt stopper. Through this stopper ran an iron rod, suspended inside a copper cylinder. To the untrained eye, they were just more ancient curiosities. But German archaeologist Wilhelm Koenig saw something more when he studied them years later. He proposed a startling theory. These objects, dating to the Parthian period around 2,000 years ago, were not simple storage containers. he believed they were primitive batteries or galvanic cells. The principle is simple, yet it hints at a profound understanding. If the jar was filled with an acidic liquid like vinegar or wine, the electrolyte would allow a chemical reaction to occur between the two different metals. Electrons would flow from the iron rod to the copper cylinder, creating a small but measurable electrical charge between them. Modern researchers who have built replicas have confirmed this, generating around 1 to 2 volts of electricity. That is not enough to power a light bulb, but it is a definite current. The question is, what would an ancient civilization do with such a subtle power source? One compelling theory is electroplating. A weak electrical current could be used to transfer a thin layer of gold or silver from one object onto another, like a statue, creating a brilliant and durable gilded surface. This would explain artifacts from the same era that show plating too fine to have been achieved by simple mercury gliding. Another possibility lies in the realm of medicine. Ancient texts speak of using electric fish to numb the pain of surgery. Could these jars have provided a more controlled form of electrotherapy, a tingling current applied to the skin to relieve aches? Skeptics offer alternative explanations, suggesting the jars were merely secure containers for holding sacred scrolls made of precious metals. The asphalt seal would have protected the contents from moisture. Yet, the specific combination of materials copper, iron, and an electrolyte is undeniably optimal for generating electricity, a fact the ancients could have stumbled upon through experimentation. Whether by accident or design, the Baghdad Battery presents a powerful case for a forgotten spark of electrical knowledge. What other small wonders, from gilded idols to miraculous medical treatments, could this ancient power source have enabled? This possibility of hidden energy connects eerily well with a series of enigmatic reliefs found deep within an Egyptian temple. Deep within the Temple of Hathor at Dendera, a stone carving defies simple explanation. Etched into a crypt wall is a massive, bulbous object held aloft by a pillar. Inside this strange vessel, a snake stretches the entire length, its head pointed toward one end. To many who see it, the resemblance is uncanny. It looks exactly like a giant, ancient light bulb. This is the Dendera light, and its interpretation has sparked a fierce debate that cuts to the very heart of how we view ancient Egyptian knowledge. Proponents of the lost technology theory, like researcher Erich von Däniken, point to the precise details in the relief. The snake, they argue, is a clear representation of a glowing filament. The pillar supporting the bulb appears to be an insulator, and a cable seems to run from the base of the device, connecting it to a box that could be a power source. They ask a compelling question: how else could the Egyptians have illuminated the vast, windowless interiors of their tombs and pyramids, where not a single trace of soot from torches or oil lamps has ever been found? Could this carving be a technical diagram of a forgotten method of illumination? Mainstream Egyptology offers a very different, symbolic interpretation. They explain that the scene depicts a foundational creation myth. The bulb is not a bulb at all, but a lotus flower, a powerful symbol of rebirth. The snake emerging from it is a serpent deity, representing the cycle of life and the moment of creation itself. The entire tableau, they argue, is a spiritual narrative, not an electrical schematic. The so-called cable is a lotus stem, and the box is a divine shrine. Yet, even with this orthodox explanation, the nagging questions persist for some. The visual parallel to modern electrical components is simply too striking to ignore completely. Could the truth lie somewhere in between? Perhaps the priests of Hathor were describing a profound spiritual concept using the most advanced technological metaphor available to them, a metaphor we have since forgotten. Whether it is a depiction of divine energy or literal harnessed electricity, the Dendera light forces us to confront the possibility that our ancestors perceived and represented power in ways we are only beginning to decipher. This quest to understand ancient power and precision leads us from the cryptic walls of an Egyptian temple to the hands of an emperor and a device that mapped the heavens with impossible accuracy. High in the Peruvian Andes, the fortress of Sacsayhuaman presents a puzzle carved in stone. Its walls are built from colossal blocks of granite, some weighing more than 100 tons, each one cut into a unique, irregular polygon. They fit together with a precision that defies belief, locked in a jigsaw so tight that you cannot slide a razor blade or even a single piece of paper between them. This is not simple masonry. It is a form of megalithic art that has endured for centuries, surviving countless earthquakes that would have leveled any modern structure. The sheer scale and perfection of this site force us to ask how the Inca, without the wheel, without iron tools, and without a written language, achieved such an impossible feat of engineering. How do you quarry, transport, and shape mountains of solid rock with nothing more than stone hammers and bronze chisels? The mainstream explanation suggests an almost unimaginable amount of patient labor. Workers would have pounded the granite with harder stones to define fracture lines, then painstakingly polished the surfaces for a perfect fit. Yet, when you stand before these walls, this answer feels incomplete. The edges of the blocks are not simply flat. They are often subtly rounded or have complex, interlocking contours that seem to require a master template, a level of geometric planning that is hard to reconcile with primitive tools. This has led to alternative theories that border on the fantastical. Some researchers propose the Inca possessed a lost plant-based solvent, a chemical agent that could temporarily soften granite to a clay-like consistency, allowing builders to mold the stones into place. Others speculate about the use of powerful sound waves or acoustic levitation, using vibrations to make the massive blocks weightless and easy to maneuver. While these ideas are controversial, they stem from a genuine bafflement at the physical evidence. The stones of Sacsayhuaman do not just sit on top of one another. They are woven together, with each block perfectly distributing the weight and stress across the entire structure, creating walls that move and settle as one during seismic events. This is engineering wisdom that we are only now rediscovering with advanced computer models. The builders understood their material and their environment on a level that seems to transcend the technology we traditionally assign to them. Were they simply master craftsmen whose skills we have underestimated, or did they possess a forgotten knowledge of stone, a technology that allowed them to work with the very bones of the earth? This same question echoes thousands of miles away, where another ancient culture left behind stonework of equally impossible precision. The stone walls of Sacsayhuaman are a marvel, but they are not alone in their perfection. Far to the south, on the high Bolivian Altiplano, lies a site that pushes the boundaries of ancient engineering into the realm of the unbelievable. This is the Pumapunku, part of the vast Tiwanaku complex. Here, the ground is littered with shattered stone, the broken remains of what was once a monumental platform, but it is not the scale that astounds visitors. It is the fragments themselves. Scattered across the landscape are H-shaped blocks, each one carved from incredibly hard andesite granite. Upon close inspection, the precision is chilling. Each block is not merely similar to the next. They are identical, as if stamped out by a machine. The grooves and notches cut into their surfaces are perfectly uniform, with crisp, flawless edges and perfect 90-degree angles that show no sign of tool marks. The holes drilled through the stone are perfectly circular and smooth, as if made by a modern diamond-tipped drill bit. This is not the work of artisans patiently pecking away with stone hammers. This looks like the output of an assembly line. The sheer consistency suggests the Tiwanaku people used a system of mass production over 1,400 years ago. How do you achieve such mathematical precision across hundreds of separate components without advanced measuring tools and metal alloys hard enough to cut the stone? Mainstream archaeology suggests this was accomplished with painstaking effort using stone tools, sand, and water for polishing. Yet, when engineers examine these stones, that explanation strains credulity. The precision is on a microscopic level. The surfaces are so flat and the corners so sharp that they imply the use of precision-guided machinery, something capable of making repeatable, identical cuts with inhuman accuracy. The blocks were designed to fit together with complex interlocking joints, forming a structure that could withstand immense weight and seismic force. This was not just art, it was high-level structural engineering. The technological leap required to go from simple stone carving to this kind of prefabricated, modular construction is immense. It forces us to ask a deeply unsettling question. Did the Tiwanaku possess a form of technology, perhaps a lost method of stone working, that allowed them to manipulate granite as easily as we mold plastic? The evidence lying in the dust at Pumapunku suggests that our timeline for the invention of advanced manufacturing may be off by more than a millennium. This recurring theme of impossible precision in stone connects to a discovery in the Middle East, where an artifact of a very different kind offers a new clue to forgotten capabilities. Centuries before the great factories of the Industrial Revolution, a brilliant mind in 1st century Alexandria built a machine that could have changed the world. His name was Heron, and his invention was the Eolipile, the world's first known steam turbine. This deceptively simple device was a sealed sphere mounted on a pair of pipes. The sphere had two L-shaped nozzles protruding from its sides. When the water inside the sphere was heated, the resulting steam rushed through the pipes into the sphere and then shot out of the nozzles. The force of these escaping jets of steam caused the entire sphere to spin, a dazzling demonstration of action and reaction, rotating at an astonishing speed. It was a direct physical proof that steam could be harnessed to create motion. Heron had unlocked the very principle that would, 1,700 years later, power locomotives, ships, and the entire transformation of the modern world. Yet in his own time, it was largely seen as a marvelous temple wonder, a philosophical toy to demonstrate the power of air and fire. We have to ask, why was this revolutionary technology left on the shelf for so many centuries? Recent scholarship suggests it may not have been just a curiosity. The rushing steam and rapid rotation could have been used to power small, automated devices in temples, creating moving statues or mysterious sounds to awe worshippers. It could have been adapted to operate simple machinery, like opening heavy temple doors, but the economic and social conditions for a full-scale industrial revolution simply did not exist in the ancient Mediterranean. Slavery provided cheap manual labor, reducing the urgent need for labor-saving machines. There was also a cultural divide between the thinkers, the philosophers like Heron, and the practical artisans who built things. Theoretical knowledge and hands-on engineering rarely came together to push such inventions into widespread practical use. The Eolipile represents one of history's greatest missed opportunities, a spark of genius that never found the right tinder to ignite a technological fire. It stands as a haunting reminder that discovery alone is not enough. It requires a society ready to embrace it. This failure to capitalize on a clear mechanical principle makes the achievements of our next ancient machine even more baffling, because its precision seems to defy the very tools of its era. The seamless stonework of Pumapunku feels almost alien in its precision. But another discovery, this one from the heart of modern California, presents a mystery that is even more difficult to reconcile with our history. In February 1961, three friends named Wallace Lane, Virginia Maxey, and Mike Mikesell were searching for interesting geodes near the town of Olancha. Mikesell, who owned a gem and mineral shop, was looking for new specimens to cut and polish. He brought a collection of rocks back to his workshop, but one particular stone was unusually hard, damaging his diamond-tipped saw blade. When he finally cracked it open, he found something impossible inside. The geode contained a ceramic cylinder with a 2 mm metal rod running through its center. The entire assembly was encased in a hexagonal shell of what appeared to be corroded copper. To anyone looking at it, the object bore a striking resemblance to a modern spark plug. They called it the Coso artifact. The mystery deepened when the object was analyzed. A geologist who examined the rock concretion surrounding the device estimated it had taken a minimum of 500,000 years to form. That number is staggering. It places the object's encasement deep in the Pleistocene epoch, a time when early humans were just beginning to use the most primitive stone tools. How could a clearly manufactured, mechanical object be sealed inside a rock that predates our entire species? The internal components suggest a level of technology akin to the early 20th century, yet it was supposedly entombed in stone for 500,000 years. Skeptics offer a more conventional explanation. They propose the object is indeed a spark plug from the 1920s, perhaps from a mining vehicle. They suggest that mineral-rich water quickly cemented it into a hard nodule, a process that can happen in a matter of decades under the right conditions, not millennia. The original finders, however, insisted the rock layer where it was found was ancient. The debate itself highlights a fundamental conflict. If the geological dating is even remotely correct, the implications are world-shattering. It points to a civilization with advanced technical knowledge existing on Earth long before recorded history, or it invites even more speculative ideas about extraterrestrial visitors leaving behind traces of their technology. The Coso artifact remains a powerful symbol of an out-of-place artifact, an object that simply should not exist. It forces us to confront the uncomfortable possibility that our planet's technological history is not a straight line, but a series of cycles with advanced knowledge rising, being lost, and then being buried by time itself. This profound challenge to our chronological certainty finds a strange echo in a different kind of artifact, one not of stone and metal, but of pure, impossible astronomical data. Buried within the ruins of an Assyrian palace for nearly 3,000 years, a small piece of rock crystal waited to be found. In the 1850s, archaeologist Austin Henry Layard uncovered it at the ancient site of Nimrud. It was not a jewel or a piece of decorative inlay. It was a carefully ground oval of crystal with one flat face and one convex face that curved outward. To any modern eye, its purpose is instantly recognizable. This was a lens. The Nimrud Lens, as it became known, could magnify small objects when held at the right distance. It could also concentrate sunlight into a bright, hot point capable of starting a fire. This simple fact is what makes it so revolutionary. We have long believed that the first optical lenses were developed in Europe around the 13th century, leading to the invention of eyeglasses and eventually the telescope. Yet here was a functioning ground optic created by Assyrian craftsmen around 700 years before the Common Era. The precision required to grind this crystal into a perfect, magnifying curve suggests a sophisticated and entirely unexpected understanding of light and optics. This was not a piece of naturally formed crystal that happened to magnify. It was a deliberately manufactured optical instrument. But what was its true purpose? Some scholars argue it was a decorative piece, perhaps set into furniture. Others see it as a tool for an artisan, a magnifier for fine engraving work. Yet the most tantalizing theory comes from the Italian scholar Giovanni Pettinato. He proposed that the lens could have been part of a compound optical device, the core component of an ancient telescope. This is not as far-fetched as it might sound. The Assyrians were meticulous astronomers, recording detailed observations of the planets and stars. How did they achieve such accuracy with the naked eye alone? If they possessed even a simple telescope, their ability to track celestial movements would be instantly explained. Imagine an Assyrian astronomer peering through a tube fitted with this lens, seeing the craters of the moon or the moons of Jupiter for the first time in human history. It is a breathtaking possibility. The Nimrud Lens forces us to reconsider not just what the ancients could build, but what they could see. Their world and their universe may have been far more detailed and expansive than we ever imagined. This leap in optical technology suggests a hidden lineage of scientific observation, a forgotten path of discovery that makes the function of our next ancient device, a map of the stars carved in metal, seem all the more plausible. Nearly 2,000 years ago, in the year 132 of the Common Era, a Chinese scholar and inventor named Zhang Heng unveiled a device that seemed to possess a supernatural sense. It was a magnificent bronze urn adorned with 8 dragon heads, each one gazing in a cardinal direction. Below each dragon, a bronze toad sat with its mouth open, waiting. This was not a ceremonial object. It was the world's first seismoscope, an instrument designed to detect earthquakes from hundreds of miles away. The principle was as brilliant as it was elegant. Inside the sealed vessel, Zhang Heng had suspended a heavy inverted pendulum. When the faint, telltale tremors of a distant quake traveled through the ground, the pendulum would swing. But it was not a simple back and forth motion. The pendulum was connected to a clever system of levers and linkages. It would trip only one specific mechanism, which in turn would release a bronze ball from the mouth of the dragon facing the direction of the earthquake. The ball would drop with a loud clang into the mouth of the waiting toad below, alerting the emperor's court to both the occurrence and the bearing of the disaster. Imagine the scene in the imperial palace. One day, a ball suddenly drops from the dragon facing west. The court officials are skeptical, as no tremors are felt in the capital city. But days later, a messenger arrives from a western province reporting a devastating earthquake. The device had been right. Modern engineers who have built and tested reconstructions based on the limited historical descriptions have confirmed it works with startling accuracy. The exact internal configuration remains a subject of debate, but the outcome is undeniable. Zhang Heng had harnessed a fundamental understanding of physics and inertia to create an early warning system of profound sophistication. How did he achieve this without any modern understanding of seismic waves or plate tectonics? His genius lay in observing the effects of energy traveling through the Earth and devising a mechanical means to interpret its direction. This was not guesswork. It was precision instrumentation, a tool for measurement that would not be equaled for over 17 centuries. The existence of such a device forces us to expand our definition of ancient science. It was not merely about philosophy and observation. It was about building machines that could see what human senses could not, extending our reach into the invisible forces that shape our world. Within the ruins of the Minoan palace of Phaistos on the sun-drenched island of Crete, an Italian archaeologist made a baffling find in 1908. It was a simple, fired clay disc about 6 inches across, and it was unlike anything ever seen before. Both of its faces were covered with a continuous spiral of strange, pictographic symbols pressed neatly into the clay. There were men running and women's heads, shields and arrows, birds and flowers, 45 distinct signs in total, arranged in groups that seemed to form words. The Phaistos Disc was not carved by hand. Each symbol was stamped into the soft clay with a separate, pre-made seal, a piece of type. This single object represents what appears to be the world's first known use of movable type printing, a revolutionary information technology that would not appear again until the time of Gutenberg in Europe, more than 3,000 years later. Think about the process this implies. An unknown Minoan artisan did not simply draw these symbols. They first had to meticulously carve 45 different punches, each one a precise, mirrored stamp. Then they carefully arranged them in sequence, impressing them one by one to form a coherent message spiraling inward from the edge of the disc. This was not an experiment in art. It was a system, a method for replicating language with standardized parts. The technological leap is immense. It suggests a society on the cusp of a communication revolution, one that could have led to the mass production of written records, of administrative documents, or even of literature. Yet, this is where the mystery deepens. No other example of this printing technique has ever been found in Crete or anywhere else in the Minoan world. The punches themselves have vanished. Why would such a brilliant invention appear only once and then disappear completely for 3 millennia? Linguists have tried for over a century to crack the code of the disc's 242 symbols, but without a bilingual text or a longer sample for comparison, the message remains stubbornly locked away. Was it a religious hymn, a legal treaty, a king's list, or an epic story? We have no way of knowing. The very purpose of this technological marvel is a secret it refuses to surrender. The Phaistos Disc stands as a haunting paradox, a clear artifact of advanced information technology that led absolutely nowhere in its own time. It is a brilliant, isolated spark in the darkness, a single frozen moment of genius that makes us wonder what other keys to ancient knowledge have been lost forever. This theme of a single, inexplicable device carrying a lost message finds a powerful parallel in a much larger artifact, one that seems to encode the very movements of the heavens into its design. Deep within the jungles of Costa Rica, a different kind of stone mystery emerged from the soil. During the 1930s, as the United Fruit Company cleared land for banana plantations, workers began to uncover incredible objects, massive stone spheres perfectly round, some half buried in the earth as if they had grown there. These were the stone spheres of the Diquis Delta, created by a pre-Columbian culture over 1,500 years ago. Their sizes vary dramatically, from small spheres the size of a tennis ball to colossal giants over 2 meters in diameter, weighing more than 15 tons. The sheer scale of the largest spheres is breathtaking, but it is their precision that truly confounds archaeologists. How do you carve a block of hard granite into a near-perfect sphere using only other stones? The mainstream theory suggests that ancient artisans first roughly shaped the boulders by heating them with fire and then rapidly cooling them with water to fracture the surface. Then, using hammerstones made of an even harder rock, they would have painstakingly pecked away at the surface, slowly rounding the form. Finally, they would have polished the sphere for a smooth finish using sand and leather. It was an unimaginably laborious process, requiring generations of patient work for a single large sphere. Yet, when you look at modern measurements of these stones, the results are staggering. Many are so perfectly spherical that their measurements deviate by less than 2 centimeters across their entire surface. This is not just a rough ball shape. This is a degree of geometric precision that suggests the makers possessed a profound understanding of form and volume. They had to maintain a perfect curve in 3 dimensions without the use of modern measuring tools or mathematical instruments. How did they ensure consistency? Some researchers believe they used a system of strings and plumb bobs to constantly check the curvature, a painstaking form of quality control that required advanced spatial reasoning. The purpose of these enigmatic objects remains a subject of fierce debate. Were they astronomical markers arranged to point to celestial events? Some spheres have been found in alignments that correspond to solstices or equinoxes. Were they symbols of power placed near the homes of chiefs to denote status and authority? Or did they hold a deeper cosmological meaning, representing the planets or the perfect forms of their gods? Whatever their purpose, the stone spheres stand as a monumental achievement in stoneworking. They represent a culture that valued abstract perfection and possessed the technical skill to impose that perfection on the most stubborn of materials. This drive to encode complex geometry into stone finds its ultimate expression in a structure on the other side of the world, where the very walls themselves seem to be a map of cosmic forces. A single piece of weathered wood found in the ruins of a Norse convent on Greenland's Unatok Island holds the secret to one of history's greatest seafaring adventures. This wooden disc, fragmented and worn, is no ordinary plate. Etched into its surface are not decorative patterns, but a series of precise notches and a central gnomon hole, the telltale signs of a sophisticated navigational instrument. For the Vikings who dared to cross the treacherous North Atlantic in open longboats, this was their guidance system, a sun compass that turned the sky itself into a map. On a clear day, a pin placed in the center of the disc would cast a shadow. As the sun moved, that shadow would sweep across the carved markings. A skilled navigator could not only tell the time, but more critically, could find true north. By aligning the disc so the shadow fell on the correct notch for that specific time of day and time of year, a captain could hold a steady course across the featureless ocean. But the North Atlantic is rarely clear. How do they navigate under the thick, cloudy skies that are so common there? This is where legend meets science. Norse sagas speak of a magical sunstone, a crystal that could locate the sun even when it was completely hidden by cloud or fog. For centuries, this was dismissed as myth. Then, researchers identified a type of crystal common in Scandinavia, Iceland spar, a form of calcite that possesses a remarkable property known as birefringence. When you look through this crystal, it splits light into two beams. By rotating the stone until the two beams are of equal brightness, a navigator can pinpoint the exact position of the sun, even when it is completely invisible to the naked eye. The Unatok disk, used in tandem with such a sunstone, formed a complete all-weather navigation system. A navigator could use the sunstone to find the sun's bearing, then set the wooden disc accordingly to maintain that course for hours. This was not guesswork. It was a complex, integrated technology that combined astronomy, mineralogy, and practical engineering. This system explains the impossible voyages of the Vikings, their ability to reach Iceland, Greenland, and even the coast of North America centuries before Columbus. They were not just brutal raiders, they were master mariners with a technological edge that would not be surpassed for hundreds of years. How many other wooden discs, now lost to decay, once guided ships to new worlds? This mastery of the seas raises a profound question about the limits of ancient travel, a question that finds its ultimate expression in a set of maps that should not have existed. The Antikythera Mechanism's true genius lies not in its bronze gears, but in the cosmic truths they calculated. This was a machine that could see into the future, predicting celestial events with a precision that should have been impossible for its time. It could plot the erratic paths of the 5 known planets against the background of fixed stars, a task requiring an intricate understanding of their retrograde motion, the illusion where planets appear to loop backward in the night sky. To achieve this, the device employed a breathtaking piece of engineering known as a differential gear, a complex assembly that calculates differences in rotation. This technology would not be seen again until the 19th century, inside the steering mechanisms of automobiles. The mechanism used this to model the moon's subtle irregularities, its varying speed as it orbits our planet. One gear represented the moon's average motion, while another, connected through a pin and slot device, introduced the necessary wobble and speed change to match reality. It was a mechanical computer solving a 2,000-year-old astronomical equation. Recent high-resolution CT scans have peeled back another layer of its mystery, revealing a finely calibrated dial on the back of the device dedicated to the Saros cycle. This is a period of approximately 223 months, after which the Sun, Moon, and Earth return to the same relative positions, causing eclipses to repeat in a predictable pattern. The mechanism could not only warn of an upcoming eclipse but could predict whether it would be lunar or solar, and even the time of day it would occur. The mathematical knowledge required to encode these cycles into interlocking bronze gears is staggering. It speaks of a Hellenistic world where astronomy and high engineering had fused, creating a tool that was both a scientific instrument and a philosophical statement about an orderly, predictable cosmos. What other secrets did this ancient computer hold? Did it track the movements of distant stars or the passing of comets? The Antikythera Mechanism forces us to replace our image of the ancient philosopher gazing at the stars with that of an engineer, hand-cranking a universe of brass and precision, possessing a depth of astronomical understanding that would be lost for over a millennium. Standing over 7 meters tall in the heart of Delhi, a massive iron pillar has defied nature for more than 1,600 years. Forged from a single 6-ton piece of wrought iron around the year 400 of the Common Era, its very existence is a marvel, but its true mystery lies in its flawless skin. In a city subjected to scorching heat and drenching monsoon rains, any modern iron structure would have turned to a brittle, flaking shell of rust within a few decades. Yet this ancient column remains almost entirely uncorroded, its surface smooth and dark, bearing only the faintest patina of time. This is not a matter of luck. It is a testament to a lost science of metal. Modern metallurgists who have analyzed the pillar discovered its secret lies in its unique chemical composition. The ancient Indian blacksmiths who created it used a process that resulted in an unusually high phosphorus content and a very low sulfur content. When the pillar was first forged, this phosphorus reacted with the iron and the oxygen in the air, forming a thin, invisible protective film called a passive layer. This layer, only a few millimeters thick, acts as a permanent, self-healing barrier. If the surface is scratched, the phosphorus-rich metal just below reacts with the air to form a new protective coat, sealing the wound. Modern steel production, in contrast, typically removes phosphorus as an impurity because it can make steel brittle under certain conditions. We have only recently begun to understand and appreciate the sophisticated balancing act the ancient metalworkers achieved. They somehow knew how to harness phosphorus to create a rust-proof alloy, a knowledge that was completely lost for centuries. This leads to an even more profound question. How did they manufacture such a colossal object in the first place? Creating a single piece of wrought iron this large required a feat of industrial-scale smelting. Historical accounts suggest they may have used massive clay furnaces, firing them with charcoal and manually operating giant bellows to reach the necessary temperatures. Workers would have had to weld smaller pieces of iron together in a monumental effort, hammering the white-hot metal into a single, seamless column. The Iron Pillar of Delhi is more than a monument. It is a physical lesson in chemistry and engineering, a relic of a time when artisans possessed a deep, intuitive mastery over materials. It forces us to wonder what other secrets of metallurgy, what other recipes for superalloys or techniques for manipulating metal were known in the ancient world and then vanished from memory. This profound understanding of material science finds a strange and powerful echo in a much colder part of the world, where another civilization worked with metal in ways that seemed to defy the capabilities of their time. The air inside the temple would shift as the altar fire roared to life. Unseen to the worshippers below, a simple yet brilliant chain reaction was beginning. Heat from the flames expanded the air inside a sealed altar, forcing it through a pipe and into a hidden bronze vessel. This vessel, acting as a primitive pressure tank, pushed water into a large bucket. The bucket, now heavy with water, began to sink. It was connected by ropes to a series of axles and spools, and as it descended, it turned the central spool. This rotating spool was directly linked to the massive stone doors of the temple, slowly drawing them open without a single human hand touching them. After the service, the process reversed. As the altar fire died down, the air inside cooled and contracted, creating a vacuum that siphoned the water from the bucket back into the vessel. Now lighter, the bucket was lifted by a heavy counterweight, winding the ropes back the other way and gracefully closing the doors. This was the genius of Heron of Alexandria, the same inventor who created the steam turbine. His automatic temple doors were not just a clever trick, they were a masterclass in applied physics, combining principles of pneumatics, hydraulics, and mechanical engineering into a single, seamless performance. The entire system was designed for one primary purpose: to create awe, to convince the faithful that the gods themselves were opening the temple gates, welcoming them inside. And it worked perfectly, yet this leads us to a difficult question. Why was this incredible automation only ever used for religious theater? The priests of Alexandria possessed the fundamental components of a steam engine and programmable automation, technologies that could have powered mills, pumped water from mines, or mechanized workshops. But the economic and social landscape offered no incentive. Human and animal labor was cheap and abundant, while the cost and complexity of building and maintaining such machines for purely practical purposes was immense. The intellectual class often viewed manual labor and machinery with disdain, seeing it as separate from the pure pursuit of philosophy. So this spark of automation remained just that, a spark, never catching fire in a world that had no need for its heat. It is a haunting testament to the fact that a society can possess a technology without truly embracing its potential. This deliberate use of engineering for spectacle stands in stark contrast to our next device, a machine born not from the desire to inspire wonder, but from the absolute necessity of survival. While modern sea walls crumble within decades, Roman harbors like the port of Caesarea stand unyielding after 2,000 years of relentless waves. The salt water that eats away at our modern concrete has only made these ancient structures stronger, a paradox that has baffled engineers for centuries. Our modern concrete is a blend of cement, sand, and aggregate, but it has a critical weakness. When seawater seeps into its pores, it reacts with the materials inside, creating expansive crystals that generate micro cracks from within. Over time, these cracks spread, letting in more water and accelerating the decay until the structure fails. The Roman formula was radically different and brilliantly simple. They mixed lime and volcanic ash, specifically a type of ash from the Italian town of Pozzuoli, with chunks of volcanic rock. This created a robust, durable mix, but the real magic happened when this concrete was submerged. Seawater, which is so destructive to our materials, was the final, crucial ingredient for the Romans. it triggered a slow, long-term chemical reaction within the concrete. As water penetrated the mixture, it dissolved the volcanic crystals and the lime. These components then recrystallized, forming tiny, interlocking plate-like minerals that filled the pores and any nascent cracks. This process, known as post-pozzolanic reactivity, is a form of natural, continuous self-healing. The concrete does not just resist the sea, it integrates with it, using the seawater's chemistry to become denser and more resilient with every passing century. Scientists at labs around the world have only recently confirmed this mechanism using advanced X-ray imaging. They watched as the ancient recipe created a built-in repair system, a feature modern engineers are desperately trying to mimic with synthetic fibers and bacteria. The Romans achieved it with volcanic dirt and seawater. This was not an accident. It was a profound, empirical understanding of material science, a recipe perfected through observation and scaled across an empire. The knowledge of how to make this super-concrete vanished with the fall of Rome, and we have spent the last 1,500 years trying to catch up to their mastery. What other architectural secrets, what other formulas for resilience were lost in the collapse of their vast engineering tradition? This mastery over materials on a colossal scale finds a strange parallel in a device of a much smaller, more intricate nature, a machine designed not to withstand the elements, but to chart them with impossible accuracy. While a Roman chariot required a driver to hold the reins, an ancient Chinese vehicle possessed a mind of its own. In the 3rd century of the Common Era, Chinese engineers created the south-pointing chariot, a mechanical marvel that defied logic. This ornate carriage, often presented as a gift to emperors, featured a central figure of a man with an outstretched arm. No matter how the chariot turned, twisted, or circled, the figure's finger remained unerringly pointed toward the south. It was a mechanical compass, a navigational wonder that maintained its orientation with absolute certainty. The secret to this impossible consistency was hidden inside the carriage body, a complex system of differential gears. This ingenious assembly was connected to the chariot's 2 wheels. When the chariot moved in a straight line, both wheels turned at the same speed, and the gears worked in unison, keeping the pointer locked in place. But when the chariot turned a corner, the wheels began to rotate at different speeds. The outside wheel had to cover more ground than the inside one. This is where the differential gear performed its magic. It automatically calculated the difference in rotation between the 2 wheels, making a precise adjustment to the central mechanism that rotated the figure in the exact opposite direction of the turn. If the chariot turned 90 degrees to the left, the gears would command the figure to rotate 90 degrees to the right, perfectly cancelling out the movement and keeping its arms steadfastly aimed to the south. This was mechanical computation in its purest form. The gears were performing a physical calculation, solving a problem of relative motion in real time. The principles at work here are identical to those in the differential of a modern automobile, which allows the drive wheels to spin at different speeds during a turn. Yet this understanding of geared computation would not appear in Europe until the Renaissance, over 1,000 years later. How did Chinese engineers conceive of such a sophisticated system without the advanced mathematics we assume is necessary? They likely developed this knowledge through pure mechanical intuition, through a process of building, testing, and observing how gears interact. They were thinking with their hands, translating the abstract concept of direction into the tangible language of wood and bronze. This was not merely an imperial toy, it was a profound demonstration that complex problems could be solved not with numbers, but with machinery. It represents a parallel path in the history of technology, one where computation was mechanical long before it became digital. This legacy of intricate geared calculation finds its ultimate expression in another ancient device, one that did not just point the way but mapped the cosmos itself. The same mind that automated temple doors also found a way to monetize the divine. Hero of Alexandria strikes again, this time with a device that feels startlingly modern, a coin-operated machine for dispensing holy water. Imagine a temple visitor in 1st century Alexandria approaching a sealed vessel of sacred water. They would drop a 5-drachma coin into a slot. The coin would fall onto a delicate pan, a tiny lever scale. The weight of the coin would tilt this pan, pulling a string that, in turn, opened a valve just long enough for a precise measure of holy water to flow out. Then the coin would slide off the pan, the lever would reset, and the valve would snap shut, ready for the next pious customer. This was not just a clever trick, it was the world's first vending machine, a perfect fusion of commerce, convenience, and religion. The underlying principle is the same one used in every snack and soda machine today, a system that verifies payment before delivering a product. Hero had mechanized a sacred transaction, ensuring that every offering was met with an equal and measured reward. The sophistication of this commercial automation is what makes it so poignant. The ancient world was standing at the very threshold of a mechanized economy. They had the technology to create automated marketplaces, to standardize trade, and to reduce the need for constant human oversight in simple transactions. Yet, like his steam engine and automatic doors, this invention remained a temple curiosity, a wonder meant to inspire awe rather than to revolutionize daily life. The social and economic structures were simply not there to support its widespread adoption. Cheap labor and a culture that separated philosophical invention from practical business application kept it confined to the realm of religious spectacle. What other automated systems might these ancient minds have conceived? Could there have been coin-operated grain dispensers in public markets, or automated toll booths at city gates? We will never know because the spark of this particular technological path was never allowed to catch fire. This recurring pattern of brilliant, isolated inventions forces us to confront a much larger and more unsettling question about the very nature of progress itself. A swordsmith in medieval Damascus could produce a blade so legendary, its reputation still echoes today. These were not just weapons, they were masterpieces of material science, forged from a unique type of steel known as woots. This steel originated in India, made from iron ore with specific, rare impurities. The smiths would melt this iron with charcoal in a sealed clay crucible, a slow heating process that allowed carbon to dissolve evenly into the metal, creating a steel ingot shot through with a delicate, tree-like pattern of iron carbide. This ingot was the raw material for a miracle. The true genius of the Damascus smith lay in the forging. They would heat the woot steel ingot to a precise, glowing temperature just below its melting point. Then, with expert, rhythmic hammer blows, they would carefully draw the metal out into a blade. This was a dangerous dance. Heat it too much, and the beautiful carbide pattern would be lost. Heat it too little, and the steel would crack. The smith was not just shaping metal, he was manipulating its very crystalline structure. Through this controlled, painstaking process, he created a blade with a seemingly impossible combination of properties. It was incredibly hard, allowing it to take and hold a razor-sharp edge that could reportedly slice a silk scarf floating on air. Yet it was also remarkably flexible and tough, able to bend without permanently deforming and resist shattering upon impact with another sword or armor. The distinctive, swirling, watery pattern on the surface was not merely decorative, it was a visual signature of this complex internal nanostructure, a map of the ultra-hard carbide particles embedded within a softer, more flexible steel matrix. This knowledge vanished around the 18th century. The exact ore sources were lost, and the intricate, almost ritualistic forging techniques died with the master smiths. For centuries, modern metallurgists tried and failed to recreate it. They could make steel just as hard, but it would be brittle, or they could make it flexible, but it would not hold an edge. They could not replicate the perfect, seemingly contradictory balance. The breakthrough came only recently with the advent of powerful electron microscopes. Scientists were finally able to peer into the steel at an atomic level. They discovered that the ancient smiths had, consciously or not, been working with nanotechnology. The forging process created carbon nanotubes and nanowires within the steel, incredibly strong microscopic structures that reinforced the blade, giving it its legendary strength and resilience. This was not magic, it was a level of material engineering that we have only just begun to understand with our most advanced tools. The loss of Damascus steel is a haunting reminder that technological peaks can be isolated and temporary. It forces us to wonder what other material secrets, what other recipes for super strong alloys or methods for manipulating matter at the smallest scales were discovered in ancient forges and then vanished into the ashes of history, leaving behind only a legendary blade as a clue. The Antikythera Mechanism is more than a singular marvel, it is the ultimate historical anomaly. This device should not exist within our understanding of ancient Greek technology. Its very gears encode a devastating truth, that its creators possessed a sophisticated grasp of mathematics, astronomy, and precision, engineering that historians believed would not emerge for another 1,000 years. The machine's design reveals a deep understanding of complex lunar motions and planetary cycles, knowledge that required not just observation, but the ability to translate celestial patterns into precise mechanical ratios. The gear trains are a physical form of calculus, solving astronomical equations with turning bronze. This was not the work of a lone, brilliant tinkerer. The sheer refinement of the mechanism, with its compact design and interlocking functions, marks it as a mature technology. It feels like a product of generations of development, a model that implies the existence of simpler, cruder predecessors that have been lost to time. So where are those earlier prototypes? Where are the other devices? Their absence is as loud as the mechanism's ticking. The most chilling part of this story is not its creation, but its disappearance. This entire branch of advanced engineering, this path toward mechanical computation, simply vanished from the historical record for over a millennium. When devices of similar complexity finally reappeared in medieval Europe, they were starting from scratch, unaware that the ancient world had already solved these problems. What could cause such a profound and specific amnesia? Was it the collapse of the Roman Empire and the burning of libraries like Alexandria, where this knowledge might have been stored? Was it a shift in cultural priorities, where practical engineering was deemed less valuable than philosophy or theology? Or does the answer lie in the sea itself, with countless other ships carrying similar wonders now resting in unmarked graves on the ocean floor? The silent fate of the Antikythera Mechanism forces a humbling conclusion. Our linear timeline of human progress is an illusion. Technological advancement is not a steady climb upward. It is a fragile flame, easily extinguished, and the history of invention is likely a story of countless cycles, of brilliant sparks that glowed brightly for a moment before being swallowed by the dark. These scattered anomalies across time and space are not merely a collection of curiosities. They form a disturbing pattern, one that challenges the very foundation of our historical narrative. From the geared computer in a Greek shipwreck to the rust-proof iron in India and the precise stonework of the Andes, we see a consistent theme of sophisticated knowledge appearing, flourishing in isolation, and then vanishing without a trace. Why would so many different cultures with no apparent contact develop such advanced technologies only to let them slip away? Mainstream archaeology offers a compelling, if sobering, explanation. It suggests that technology is not an inevitable upward climb, but a fragile ecosystem. Each of these inventions was a solution to a specific local problem, born from brilliant empirical observation. The Antikythera Mechanism answered a deep cultural need to understand the cosmos. The Roman concrete solved the practical problem of building eternal harbors. But without a supporting infrastructure of widespread education, stable economies, and a culture of continuous innovation, these technologies remained vulnerable. They were the prized secrets of a single guild of craftsmen, or knowledge locked away in a library that could burn. When that civilization faced war, famine, or social collapse, the delicate chain of transmission was broken, and the knowledge simply died with its last practitioners. This view sees these artifacts not as fragments of a global lost civilization, but as isolated peaks of human ingenuity that were eventually eroded by time. Yet, the sheer number of these peaks gives other researchers pause. Could there be a different story? Some theorists propose that these are not isolated events at all, but the scattered remnants of a much older, foundational civilization, a sophisticated culture lost to a prehistoric cataclysm whose survivors seeded advanced concepts across the globe. Others suggest a more gradual transfer of knowledge along forgotten trade routes, with ideas slowly diffusing from a single source, being adapted locally, and then being lost at the source. The most speculative theories even point to the possibility of contact with outside, non-human intelligences, though this remains firmly in the realm of speculation. Perhaps the truth is less dramatic but equally profound. Maybe we have severely underestimated the innovative capacity of the human mind in the ancient world. These artifacts may not be proof of a single lost world, but evidence that the spark of genius has always been with us, igniting repeatedly in different times and places whenever conditions were just right. They represent parallel paths of discovery that were ultimately cut short. This pattern of technological rise and fall forces a humbling conclusion. Progress is not a one-way street. It is a cycle. A society can possess the blueprint for a steam engine and use it only as a toy. It can understand the principles of electricity and never build a power grid. It can chart the stars with a mechanical computer and then forget how to make one for 1,000 years. The history of technology is not a straight line leading to us. It is a story of brilliant detours and dead ends, of forests of knowledge that burned down, leaving behind only a few charred seeds. What does this mean for our own technological civilization? Are we standing on an unshakable peak, or are we just another temporary flare in the long, dark night of history, destined to become a mystery for some future culture to unearth and wonder at? These 20 ancient machines form a constellation of mysteries scattered across time and geography. Together, they present a powerful challenge to the comforting story of a straight, unbroken line of human progress from primitive beginnings to our modern pinnacle. The evidence laid out by these artifacts suggests a very different rhythm to history, one of brilliant flashes of innovation that flare up, illuminate a culture, and then are extinguished, often for centuries or even millennia. Mainstream archaeology works diligently to find conventional explanations for each individual puzzle, and many of these explanations are compelling. Yet when you step back and look at the cumulative picture, a 2,000-year-old computer, a rust-proof iron pillar, stonework of impossible precision, and steam power used for temple wonders, a pattern emerges that is difficult to ignore. It points to a recurring theme of sophisticated knowledge, of capabilities we have consistently underestimated in the cultures that came before us. The true lesson here may not be about proving a single lost civilization, but about cultivating a profound sense of humility. We must accept that our ancestors were not primitive. They were brilliant problem solvers whose empirical understanding of the world could, at times, achieve technological heights that would not be reached again for ages. Their knowledge was fragile, often held by small groups of artisans or stored in libraries vulnerable to fire and conquest. A single war, a famine, or the slow collapse of an empire could sever the chain of transmission, and a technology would vanish as if it had never been. This cyclical view of history forces us to look at our own technological civilization in a new light. Are we the inevitable endpoint of progress, or are we simply another bright flare in the long human story, one that future archaeologists might one day piece together from the fragments of our smartphones and satellites? The enduring enigma of these ancient machines is an invitation to keep questioning, to keep exploring, and to never stop marveling at the incredible, recurring ingenuity of the human spirit.